Okay, so what you should already know. So this is related to the energetics unit from year one. So there's no real need for me to go over this. If you don't recognize any of this, you need to go back and you need to look at your notes from the energetics unit, which was unit 8. So enthalpy change, just be careful about your use of the word enthalpy and energy. And we know that the enthalpy change is essentially the energy change, but it's at set constant pressure. Okay. Next, Hess's law. Again, you should understand this definition. You should be able to apply it verbatim. So there's no need for me to go over this, but understanding Hess's law is key to understanding everything that we're going to do now. So enthalpy change is really important, and Hess's law, again, really important. We need to make sure that we understand both of those. Okay, so what we're going to use are Born-Haber cycles. And Born-Haber cycles, I think actually once you get your head around them, they're actually a lot easier than the sort of diagrams you've been looking at with Hess's law. Even though there's more to them in terms of the number of components, I think once you understand what we're looking at, you will basically access them a lot quicker. And as it says there, they're developed by two of the 20th century's most important scientists. So we've got Max Born, say hello Max, hello, and Fritz Haber, say hello, hi. Okay, so we've got some definitions coming up. So this first lesson is just basically a whole sort of list of these definitions that you have to remember. And where it says verbatim, that means you just have to be able to quote them directly. And you don't use any of your own definitions, you use the ones that are provided either in the book or in this video. The point of learning them verbatim is that you will pick up more marks. If you're unsure of your definitions, if you can't produce these definitions word for word, you're going to struggle to pick up the marks on the test. So basically, not only will you lose marks, you'll get lost within the unit. So make sure, and this is the main part of this lesson, make sure that you learn these definitions and you're able to either provide a definition if asked for it, or recognize a definition from within an equation. Okay, as you can see, this is from year one. This is an AS definition for enthalpy change. The main thing to recognize here is that if we ever see this symbol, we've got standard conditions, pressure, temperature. I've included solutions because this comes up later on in another unit that we look at. But basically the temperature and the pressure are key for us when we're looking at this thermodynamics unit. But it's not a bad idea to actually get used to remembering that solutions of 1 mole per decimeter cubed, that's included in standard conditions. From year one, we can look at the enthalpy of formation. So this will just be a review. Now it's really important that you understand that when we're looking at the definitions, they all follow a similar pattern. So we're always concerned with 1 mole of something. So here we've got 1 mole of a compound is formed from its elements. So if it's formed, we're looking at the right hand side of the arrow. So we're looking at the formation here of sodium chloride. So 1 mole of a compound, that is 1 mole of a compound. We got its elements under standard conditions. So again, standard conditions for sodium are solid, chlorine is a gas. If we don't see 1 mole formed, if we saw maybe 2 moles formed, we'd have to sort of double this value. But again, then that would not fall under the definition for our enthalpy of formation because we wouldn't have 1 mole. So just remember that if you're not seeing 1 mole formed, it's not going to be the enthalpy of formation, so you're not going to be able to use the value that is provided. Okay, we can look at the enthalpy of combustion, again a year one topic. When we're looking at this, we look at 1 mole of a substance completely combusted in oxygen under standard conditions. So the methane, 1 mole of methane, completely combusted with oxygen, to give us this enthalpy change, so to give us this value. Remember, again, with this, if we don't see 1 mole here, we can't use this value. So if we see 2 moles, we would have to double this value. So what we're going to move into now is we're going to learn some more definitions, some new definitions for this unit. Now they're fairly straightforward if you just take time to actually listen to the definition and think about it. So we're thinking about now the standard enthalpy change of atomization. So what you need to think about is, you know, what's going on with atomization, and the clue is in the definition. During atomization, we are making atoms. So again, the enthalpy change when 1 mole of gaseous atoms is formed from the element in its standard state. So it's actually an even easier definition to learn and to remember. This would be an equation that relates to the enthalpy of atomization. So we've got 1 mole of gaseous atoms formed. So we've got sodium atoms being formed because the gaseous, if you remember back to year 7 and you remember your particle theory, you know, your solid, liquid and gases diagrams, you should remember what the particle model for a solid looks like, a liquid looks like, and gases. And in a solid, the particles are all fixed together and they're all vibrating. And if you think about a gas, the particles are separate from each other, they are all moving freely. So when we consider this, it's important to actually get a sort of try and visualize what's going on. So we go from a solid to a gas. Here, this is also atomization because we have got individual oxygen atoms, whereas before we had O2, an O2 molecule. We are now getting oxygen atoms on their own. So again, that's important to recognize. So let's just get rid of these. Okay, so the visualization that I was talking about, that is the sodium metal as a solid. So they're all bunched up together, and this represents the gaseous sodium atoms. Try and hold on to that, try and sort of keep that in mind when you're moving forward. So we've got sodium metal, and then obviously to actually separate the atoms from each other, so to move from the solid through a liquid to the gaseous phase, we have to put energy in. So it's really important that you understand that this process is endothermic. So this was part of the energetics unit. This was part of what I wanted you to look at as revision. That you need to understand that bond breaking and bond making are different in terms of energy in and energy out. So for bond breaking, you have to put energy in, and when you've got bond making, energy is released. That's really important. So again, it's nothing new. You just have to remember to bring all of these ideas, all of these concepts that you've learned over the years, you bring them all forward into year 2. On the previous slide, we did see something that you might have picked up on, and it's the idea that for diatomic molecules like oxygen, we don't use 1 mole of oxygen molecules, because 1 mole of oxygen molecules would produce 2 moles of gaseous atoms. So here, where we've got 1 mole of the O2, so 1 mole of oxygen molecules, that would actually give us 2 moles of the oxygen atoms, and that would again go against the definition. For our definition, we need 1 mole of gaseous atoms. So for 1 mole of gaseous atoms, we only need half a mole of oxygen molecules, and that's because in the molecule we've got 2 oxygen atoms. So literally, if we started off with O2, we would produce 2 lots of oxygen atoms. That would be too many. That would be actually double the value that we're expecting to see. So just remember, if you're seeing things like oxygen, chlorine, so diatomic molecules, we only need half a mole of the gas to produce 1 mole of gaseous atoms. Again, it's really important that if you're not seeing 1 mole of oxygen atoms formed, you can't use this value of 249. If you see 2 moles formed, you'd have to double it up. Or if you 3 moles or 4 moles, you adjust accordingly. So really with these next few slides, I'm just going to let them run. And there's not really any need for me to jump in and keep commenting on them. I will, however, point out that all of these definitions, again, they're using this sort of generic template where we've got 1 mole of electrons from 1 mole of gaseous atoms. So it's 1 mole, 1 mole, 1 mole. But again, just think about your definition itself. First ionization enthalpy. So it's going to be the enthalpy change required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions with a 1+ charge. This is similar to the ionization energy work that we did in year 1. So as you can see, you link this definition, 1 mole of gaseous atoms to form 1 mole of gaseous ions with a 1+ charge. We also need to consider that this is going to be endothermic. It's an endothermic process because we have to put energy in to remove the electron, because there's electrostatic forces of attraction between the electron and the nucleus, so we have to overcome that, so i.e. we have to put energy in. So you need to see if you can conjure up this second ionization enthalpy. So have a think about a definition. You should be able to be thinking now about using words like 1 mole. And if it's the second ionization enthalpy, we're going to already start off with something that's being ionized. So we're taking the first ionization enthalpy equation as our starting point. So we would start off with an ion that has got a single charge, and we're going to remove another electron, and that will give us a 2+ ion. So you need to sort of think about how you can construct that. So again, enthalpy change, 1 mole of electrons from 1 mole of gaseous 1+ ions to form 1 mole of ions with a 2+ charge. So I've used magnesium in this case because we're not obviously going to be able to, well, we wouldn't usually ionize sodium a second time, but with magnesium, the group 2 metal, we will do that. So again, just link the definition to the equation. So we've got 1 mole of gaseous 1+ ions to form 1 mole of gaseous 2+ ions, and we're removing 1 mole of electrons. Again, endothermic process because we're removing electrons, so they're already attracted, so there is some forces of attraction that we have to overcome. The key to understanding this definition is we're talking about electron affinity. Now affinity is sort of a liking or an attraction for something, so electron affinity, it's almost the opposite of ionization. So here, instead of removing an electron, we're actually going to add an electron in. We've got, again, it's the similar generic template for the definition. 1 mole of gaseous atoms gain 1 mole of electrons to form 1 mole of gaseous ions with a 1- charge. So if you're getting used to all of these definitions, 1 mole of this and 1 mole of that forming blah 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 blah, you'll be able to work your way through. Now let's have a look. So we've got an oxygen atom, so that is 1 mole of gaseous atoms, and they are going to gain 1 mole of electrons to form 1 mole of gaseous ions with a 1- charge. The important thing to see here is that this is exothermic. Now why is it exothermic? It's because we're forming a bond. We're actually forming a bond between the incoming electron and the atom itself. So this is bond making, so that's why it's exothermic. Okay, we need to think about the second electron affinity. Again, what do you think is going to be happening here? You should be sort of be able to predict this now. That the second electron affinity, we're going to add a second electron to an ion, and that ion's already negative. So let's see if we can run through it. Enthalpy change again. So we're going to get marks for enthalpy change. 1 mole of gaseous 1- ions gains 1 mole of electrons to form 1 mole of gaseous ions with a 2- charge. Okay, so let's see if we can link that. So we've got 1 mole of gaseous ions with a 1- charge. They are gaining 1 mole of electrons, and they are forming 1 mole of gaseous ions with a 2- charge. Okay, so you either have to recognize the definition from within the equation, or you have to provide the definition outright. However, there's a small sort of caveat here with this second electron affinity. The second electron affinity is endothermic, and the reason it's endothermic, even though we're making a bond, we have to overcome the repulsion between the two negative species. So we've got a negative ion and we're trying to add a negative electron. They're not going to want to sort of come together on their own because of that repulsion. So we have to use energy. So we have to basically put energy in to overcome that repulsion. It's really important that you understand that that second electron affinity, so adding a negative electron to a negative ion, that is endothermic. So we have to put energy in. And the final one we're going to look at is lattice enthalpy. Now, because we're dealing with ionic compounds, when we're looking at Born-Haber cycles, lattice enthalpy is basically, if you imagine a giant ionic lattice, so something simple like sodium chloride. So the lattice is held together with electrostatic forces of attraction between the positive ions and the negative ions. So if we made the lattice up, so if we started to form the lattice, we are making bonds between the positive ions and the negative ions. That would be bond making, so that would be exothermic. An equal sort of amount of energy would be required to break up that lattice. So essentially, with the enthalpy of lattice enthalpy that we're going to look at, the values, lattice enthalpy formation is going to be exothermic, as I've said, because it's going to be all about bond making. If we would try and break it up, i.e. bond breaking, it's going to be endothermic, but the values are going to be the same. but depending on which way you're going. So if it's, say, exothermic and it releases 500 kilojoules per mole, when making the lattice, you would need 500 kilojoules per mole putting in to break it up. And that's the last one that we're going to look at. That's the end of the lesson. So what you need to do now is you need to go away and have a little break, write up your notes. What I would suggest you do is all of those definitions. What I would do personally is make a series of diagrams, so sort of like particle model diagrams, or represent them with pictures and labels to clearly show your understanding of each of the definitions. So don't just rewrite out the definitions on their own. It's quite flat, and it probably won't stick with you too well. So go away, and when you're writing them down, write out a definition, give an example with an equation, but then also draw a little picture to show, say, like the particles. So similar to the first one that I showed you, which was the sodium metal. So all the particles in the sodium metal as a solid then forming gaseous sodium metal atoms. Go away and do something like that. And as you can see, if you need any help, just ask.